Yeah, hey everyone. So thank you so much for having me. Yeah, unfortunately I couldn't be there in person, so I'm joining from Tokyo, where it's currently 3 a.m. So yeah, if I stop making sense at some point, you'll know why. So that probably will be well aligned with the talk about inconsistency. Okay, so I'm Natalia, and this is a joint work with my mentor Oliver Richardson. And yeah, generally today I want to talk about catching LLMs contradicting themselves. So let me first start with this example. So there is some chain of thought from some mathematical problem from a small benchmark. So the model is reasoning, solving a problem about pen pals. And here it first correctly figures out that Mike has three pen pals, 5 - 2 is 3, good. But then 2 lines later, it just uses fives instead. So it actually computed one numbers and used a different one, and finally got the wrong answer, and it contradicted itself mid-reasoning. So generally, why would we even care about this beyond some math homework? Well, the two main reasons about AI safety that I can think about. So the first one is about alignment faking. When a model might say, I refuse purely because something is harmful, when it knows that it's being watched, but then it can comply with the same request when it thinks that nobody's looking. So this kind of setup represents inconsistent stated beliefs. And the second one, so we're betting a lot on chain of thought monitoring for safety right now, but the model doesn't always mean what it says. So we need some tool to catch internal contradictions more directly. Okay, so what do you actually do about that? Well, I first take a chain of thought, then break it into some atomic claims, then figure out what depends on what, and come up with internal arcs. Then probe the model's beliefs about those dependencies. Then I compute an inconsistency metric that tells us how far are those beliefs from being jointly satisfiable. Yeah, here is like the general pipeline. And a very big disclaimer, this is very much currently still a work in progress. So yeah, I will be honest about things that doesn't work yet. There is still a plenty of those things. So the mathematical model behind all this is called a probabilistic dependency graph, introduced by my mentor Oliver together with Ja Halpern. And generally, this is a generalization of a Bayesian network. But in a Bayesian network, usually your CPDs, conditional probability distributions, live on nodes, and they all have to be consistent. Unlike that, in PDGs, the CPDs live on edges instead, and they allowed to disagree. So if you have some new information that you acquired, you can just add an edge to your graph, and you don't really have to restructure the whole thing. So this is actually exactly what makes this pretty useful for me, because it can represent inconsistent beliefs, and not only represent it, but actually we can measure how much those beliefs are actually consistent. And since it's modular, we can combine sources by merging graphs or localizing like some subgraphs where the inconsistency emerges. It also has trust parameters, and it is also a strict generalization of Bayesian networks and factor graphs. So here is the main formula. I understand it probably looks kind of dense on slide, but yes, the main idea is that for each edge, we take the Kyle divergence between the best fit joint and stated belief, then weight by our own confidence, sum over all edges, and basically, yes, this is the inconsistency measure. So yes, then there is this combined objective, and inconsistency captured belief conflict. So do the CPDs actually contradict each other? And the second term with the gamma 1 captures the structural fit, and gamma controls the balance between those two. Yeah, so now here is a really cool part from the next Oliver's paper. You can see it in a dashed box. So basically, standard ML loss functions are all special cases of this, like log loss, MSK, elbow. These three diagrams show the corresponding PDGs, and when you compute the inconsistency of those PDGs, you actually get specifically the values of those loss functions. So this is a natural information theoretic measure of belief coherence, and everything else is a special case. And yeah, the key property of inconsistency is when inconsistency is 0, the beliefs are satisfiable, but when it is above 0, there is some genuine contradiction between agent's beliefs. And because inconsistency decomposes our graphs, we actually get error maps. So we can point to where the problem is. Okay, so what I'm actually doing, let me show how this works on some specific example, also like some very simple math problem. Oh, sorry. So for step one, first I extract the variables using a stronger LLM judge. Then step two, I discover the arcs within the graph. So what I'm doing is leave one out attention. I from the set of all claims, I remove a claims and ask the model to retrieve it, and then see what gets attended to, and those become parents of this child. Then step three, this is the most hard part for me currently, is estimating the CBDs. So right now I mask all the numbers in the problem, then present parent values as known information, ask the model to predict the child. And now when I remove a parent, I actually remove this information. And for the fourth step, I compute the inconsistency measure using convex optimization. Okay, for the very first results on 500 mathematical problems and 8 billion parameter model, well, it does work for detecting the wrong mathematical solutions and separating them from the correct ones without even having any ground truths, gold labels. Though even though it is statistically significant, it is not a state of art. It is still relatively far from state of art techniques right now. But yeah, generally, honestly, detection is not the most exciting part for me. Localization is, I think, much more fun. So the node or the claim with the highest inconsistency actually matches the actual error, which we also recover from stronger LLM judges. So currently, top three accuracy, which is if I take three claims with the highest inconsistency score, it has accuracy of 64%, and comparing to a random baseline with just 11%, it clearly has some signal. So as far as I know, this is probably the only unsupervised method that gives you paragraph localization of error or inconsistency. And yeah, one thing I also wanted to flag though is that inconsistency, well, as I believe and understand, is generally the metric much richer than just using it like for error detection. But I'm just currently using binary math tasks here to validate the pipeline. But eventually, my real goal is some kind of like more soft science settings where inconsistency itself is what matters. Okay, so just two quick examples. The left one is a true positive, so model. So as in the example I had on the first slide, model computes one values and uses a different one, and inconsistency lights up on exactly the right claim. So it is a happy case. The right one is a false negative. So the model misreads the problem from the very start, but after that, every step is perfectly consistent. So the metric is inconsistency is basically zero, and each country catches. And this is actually like the key conceptual point. So inconsistency, well, even based on its name, it does measure internal consistency, but not like any epistemic correctness. We're not making any claims about so-called correctness in general. So if you start from wrong premises but reason correctly, you can still get low inconsistency. Also, if you don't have any arcs within your graph, you will also definitely get zero inconsistency. So this is quite by design. Yeah, okay. So now here where things get more interesting. I ran a diagnostic to randomize the structure or randomize the CPDs to understand what actually is behind the signal and what actually breaks. So first, when I take the random structure, everything collapses. So the structure, the arc structure that I extract using the attention is actually useful, which is the good news. And the second one, which was quite surprising for me, is that random CPDs actually work even better than the real ones originally. So why could it be the case? Well, because our initial real CPDs had a very massive yes bias. So the model just said yes to like 80% of the time, no matter what it was asked about. And at least random like uniform random values had some good variety. And the third one, this ties it together. So the results we had here is actually well connected to the intuition behind the gamma parameter. So at gamma 1, the structure dominates and the CPD values actually barely matter. And yeah, if we take a look at the scatter plot, it becomes obvious that inconsistency correlates heavily with the number of arcs. So it's basically just measuring problem complexity. Like if you get a harder problem, you get more steps and higher score. So at that point, well, I got some real signal, but it's not working precisely as I wanted it to. So it's working through a wrong mechanism. And the goal to make actually gamma equals 0 work. And for this purpose, I need much better CPDs. So yeah, that's just a continuation of the discussion I had on a previous slide. So over like 7,000 CPDs, almost half were below 5% signal. And the reason is, first, the early shaft model generally have a very heavy yes bias. And the second one is the prompting originally was not particularly good, and it revealed a lot of information. So the fix that I used after that is masking all the numbers. So right now, the present parents are known values, and all other numbers in the problem are masked. And yeah, instead of asking for yes or no tokens, I iterate over possible solutions and use logits for particular numerical solutions, which is inspired by this Fobar paper. Yeah, before that, I used a lot of other things. So 6 models, different prompting strategies, fine-tuning, but yeah, most of them just increased spread, but not discrimination. Yeah, and here is some small proof of concept. So just as for now, just trying on some particular single problems. So one arc, 3 parents fitting into total paid. When I have all the parents present, it has quite high match. When I remove material cost, it barely changes. But if I remove total cost, which is the real parent for this child, it crashes to 0. So if there are no parents at all, there is just some random noise. And this is probably exactly what correct CPD looks like, or yeah, what I initially wanted to extract. So comparing to the older approach, it has yeah, much better values. And well, this is just an example on one task. So the full evaluation on MES 500 is currently in progress. But for the first time, we're actually seeing some clear dependency signal. And that's what I needed to make gamma equals 0 work. Okay, so yeah, where does it goes? First, hopefully for the runtime monitoring. So chain of thought can be thousands of tokens, and the claim graph is much smaller and easier to review and easier to flag. Second one is interpretable localization. So not just saying that something is wrong, but actually with which particular dependency, which stated beliefs are contradicting each other. So you can hand someone an error map. The third one is the alignment auditing. So you can build a PDG across different contexts and use same model but different situations and check whether the beliefs are consistent or does it contradict itself depending on who's asking. And on the same way, you can also try to merge beliefs of different models to see how much they contradict each other. One important caveat, yeah, everything here happens as for now in verbalized reasoning, so bring into internal states is planned, but not very obvious how to do it as for now. Yeah, and quick takeaways. Here I use some principled framework for belief coherence, and it does localize errors compositionally, which is hopefully unique. So yeah, I found the CPD bottleneck and have some fix. Yeah, which is the important thing, which might seem not very obvious throughout the presentation, but the framework itself is very domain agnostic. So my next step, hopefully throughout the extension, is moving forward beyond just mathematical frameworks. And I'm interested to see how it works on moral judgment benchmarks where consistency of stated values is actually what matters most. Yeah, thank you very much, and very happy to hear your questions. Thank you.